All right, welcome, good morning. We are looking at, and you have dealt with estimating spreadsheets. I'm not going to do this basic load path estimation and sketches with Excel. What you have to realize that really is one of the better places to do lots of these things, but usually pictures need to go along with them, and as you've seen already, the ability to throw pictures into these programs is becoming more and more and more possible and kind of expected, even in the comments section. So we're looking at a problem. I'll do it again just here in terms of the identification. We had a 8-bay structure that we've talked about over and over again, and that was basically, I'm going to draw my girder lines, if you will. There's my bays here. Divide this in half, and then in half again, and then label these things A, B, C, D, and E. A, these are called your grid lines, and we're going to call this 1, 2, and 3, and very often you got this little kind of line connecting them up, and you probably have a circle around each of them, right? And then you're given some general, typically the way it starts is you're giving a use based on geography, geology, and geometry, if you would, and you're going to basically need to identify, and we'll try to do that here, the different columns and girders and beams that you're dealing with, or joists. So I'm going to change my color here now, and my width, I'll change it now to something more greeny, and I'm going to basically realize that this here, and this one here, and this one here, and this one here are corner columns. And they're basically going to take 1/4 of a bay, effectively. If these ones here, I'm going to go with a circle, 1, 2, 3, these are interior, right? These ones here, I'll do with a square, are actually one form of exterior, and they might be different than the other. And these ones here are a diamond, 1, 2, 1, 2, 3, 4, 5, 6, and these are exterior 2. In addition to that, you then have basically a set of joists which you have to decide which way they run. We'll go with that, and that's typically the way it's shown. And so you have interior, exterior beams. You have basically going from the bottom up or the top down. Let's go from the bottom up. The next thing you have is girders. You have exterior girders and interior girders. Interior girder. And then you have basically interior beams or joists and exterior or spandrel joists. These are the ones on the outside. Now you get to the question, once you've got them all identified, you can put numbers on them, 1, 2, and you can actually give them, for instance here, the corner ones are A1, A3, E1, and E3. You can go through, etc., and count them up. So if basically I'm going to lump these two together, and we're going to have 4 of these, 4 exterior, 4 corner. We're going to have interior, we're going to have 1, 2, 3 interior. Exterior, we're going to have 1, 2, 3, 4, 5, 6, 7, 8. And those all add up to 15. 1, 2, 3, 4, 5. So that's basically what you've got here. Exterior girders, you're going to have 1, 2, 3, 4. Again, you can label them. The girders would be labeled, for instance, like A1-B1, etc. And you will have 1, 2, 3, 4, 5, 6, 7, 8 of those. Interior girders 1, 2, 3, 4. And then beams and interior and exterior, you're going to have a great number of them. Now, you go about eventually having to add self-weight, but when you're looking at the loading pattern, typically you're looking at this combination of live load, dead load, wind load, etc. And in this example, or an example that we might look at, you might be given something like 40 pounds per square foot, and then plus the self-weight if someone has designed the deck. So I'm going to go plus, as an example we've done before, it's 70 pounds per square foot decking. And that would be the whole flooring, concrete, reinforced floor. So what do the sketches look like? Well, if you're looking at 6 feet on center, you have 6 square feet per lineal feet times 110 pounds per square foot equals 660 pounds per lineal foot. And so your beams interior look something like this. We use pin joints on the sides, even though they're bolted in. This is a linear load of W equals 660 pounds per lineal foot, which of course gets you to the reaction of the girder. The girders turn out to have 1, 2, 3, 4 of basically half of these beams, because the beams are sitting on the other side. So this would be the exterior or the interior. The interior has twice as big. And then the columns, depending, have something coming from this down. For instance, the interior columns have those coming from this in this direction, plus then they have 2 beams. So a column might hold up 2 girders, which it turns out to be one whole girder, and then 2 beams. So that's the whole extent of the math of this and the sketch. So I'm a bit mesmerized sometimes with how, given a whole week to go through, do this, and basically a pretty straightforward problem, how even the sketch is not there. So this basic sketch and then the mathematics that you want to do, I think you learned from estimating, and see if I can go down here a little bit, is that what? If you know the total force in all of them, total force, doesn't want me to do that, I guess. Total force down should be equal to the area times the pressure down. And that's true at any and all levels. So that's a check. That's your check. Realistically, you need to add the self-weight above. And so that self-weight would include all the, for instance, for the girders, it would include all the pressure. Girders is all the pressure plus the weight, self-weight of the beams. Columns is going to be all the pressure plus the self-weight of the beams and girders. For the foundation plates going down, it would be the columns and everything else, etc., etc. In addition to that, of course, you have the potential for wind loads, etc. All right, so I'm going to publish this out. This should give everyone some basic ability to work going forward. Again, these loads here, you can go to the ASCE, and you need to look at both the LRDF and the ASD. These kind of patterns of live load plus dead load get much more complex, and there's usually these different sets of kind of criteria. You take the worst case scenario when you go through and do it. But this general sense of coming up with, that effectively is how you come up with, and I'll go to now a new sheet. And effectively is how we end up coming with these kind of things that you see in strength of materials, where we've not completely skipped it, but that sense that you've got a force down here and then some linear load. W is pounds per lineal foot, and this is maybe P pounds. And of course, we know that the equivalent uniform load in that, if this is a span L, is equal to WL plus 2P, because it holds up twice as much. Not holds up, but I'm sorry, it does twice as much damage when it's in the center. On the other hand, you might have something like this, a girder load where you have P, 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 if that is P, your equivalent uniform load might be somewhere in the order, it's not 4P, it's more than 4P, it's less than 8P. So it's something that's in the order, equivalent uniform load is probably around 4.8 from memory times P. In other words, that's going to be in kips, right? And remember, little w equals big W divided by L. Thanks for listening.